Hello, welcome to my video on data structures. This is part 5 with queue and stack. In this video, we will talk about arithmetic expression parsing with stack. Just to recap, queue has the first in, first out behavior, and stack has the first in, last out behavior. Examples on comparing the effect of their different behaviors are perhaps the breadth-first search and depth-first search algorithms, which we will discuss later under the graph data structure. In this section, we will focus on an application of stack, where we use it to help the parsing of arithmetic expressions. Consider the arithmetic expression given here. It is given to the computer as a string. Our goal is to find a way for the computer to understand it and compute the correct result. First, we know that we cannot simply compute the expression from left to right. This is because we need to respect the precedence of different operations. For example, if we simply compute the arithmetic expression from left to right here, we get a result of 8.5. But we know that the correct answer should be 9. As a result, we need a smarter algorithm to parse arithmetic strings. We will discuss the algorithm as 3 main steps. First, tokenization. Second, infix-to-postfix conversion. And third, postfix calculation. Let's begin with tokenization. The goal of tokenization is to break the arithmetic expression into an ordered set of operands and operators. The operators are the symbols representing the arithmetic operations, for example, addition and subtraction, etc. The operands are just the numbers bind to the operators. You can see that the arithmetic expression can be decomposed into a set of operands and operators shown here. Note that the parentheses are categorized as operators here. Even though they are not typical operators, classifying them as operators would make the discussion of the algorithm easier. Tokenization can be done easily by reading the characters of the string from left to right. In general, digits are considered as operands, and the other symbols are treated as operators. There are 2 exceptions. First, the floating point should be considered as a part of an operand. Second, the negative symbol should also be considered as a part of an operand. The same symbol, when used to represent subtraction, should be treated as operators though. Now, let's discuss the second step of the algorithm, the infix-to-postfix conversion. The infix expression is what we write conventionally. For example, 3 plus 5 is an infix expression. We call it infix because the operator is written in between the 2 operands. On the other hand, the postfix expression writes the operator after the associated operands. For example, the postfix expression of 3 plus 5 is 3, 5 plus. In general, the infix expression is easier to understand for humans, while the postfix expression is easier for computers. This is why we need to perform the infix-to-postfix conversion. The infix-postfix conversion algorithm contains 3 major steps. First, initialize an empty stack, which will be used to hold operators. Second, scan the infix expression from left to right. Then, we have 2 cases to consider. If the current token is an operand, we directly write it to the output. Otherwise, if the current token is an operator, we will first pop all operators in the stack that have the same or higher precedence than the current operator and write them to the output, and finally push the current operator into the stack. The only exception is how we treat the parentheses. When the pop is initiated by a non-parenthesis operator, the pop must end if it encounters a left parenthesis. Note that the left parenthesis is not popped. When the pop is initiated by a right parenthesis, the pop will end at the first left parenthesis. Note that in this case, the left parenthesis will be popped. Finally, When all tokens are processed, pop all remaining tokens in the stack and write them to the output. Let's look at some simple examples. First, consider 3 plus 5. The first token is an operand 3. We directly write it to the output. The second token is an operator plus. Since there is no token in the stack to pop, we directly pushed it into the stack. The third token is an operand 5. We directly write it to the output. After processing all tokens, we pop the plus operator out from the stack and write it to the output. The final output will be 3, 5 plus, which is the postfix expression for 3 plus 5. Let's consider 3 plus 5 times 2. Since the handling of the first 3 tokens are similar as before, let's focus on the handling of the fourth multiplication operator. According to the algorithm, we should pop all operators in the stack that have the same or higher precedence than multiplication. However, the plus operator has lower precedence than the multiplication operator, so it is not popped. In this case, we directly push the multiplication operator into the stack. Now, let's consider left parenthesis 3 plus 5 right parenthesis times 2. And we will be focusing on the handling of the parentheses in this example. The first token is a left parenthesis. According to the algorithm, it is pushed into the stack. The fifth token is a right parenthesis, and we will pop all operators in the stack until we see its matching left parenthesis. Note that the left parenthesis is also popped. Okay, let's go back to the real infix expression. Since we have already given some examples about the algorithm, I will only focus on several cases that are worth noting. The first place is the handling of the subtraction operator. When it is read, the stack contains 2 operators, plus and multiplication. Since both of them have the same or higher precedence than the subtraction operator, both are popped and written to the output. Then, the subtraction operator is pushed. The second place is when we handle the left parenthesis. Note that the left parenthesis is a special operator, and it cannot initiate any pop, but it is simply pushed into the stack. Using the algorithm described above, we can convert our infix expression into the postfix expression shown here. Now, let's discuss the third step of the algorithm, postfix calculation. Postfix calculation takes a postfix expression as input and calculates its result. It involves the following steps. First, initialize an empty stack. Unlike the stack used in the previous infix to postfix conversion step, the stack used here is for caching the operands other than the operators. Second, scan the postfix expression from left to right. If the current token is an operand, push it into the stack. Otherwise, if the current token is an operator, pop the required numbers of operands from the stack, perform the operation, and push the result back to the stack. In our example, most of the operators are binary operators, which means the required number of operands is 2. For some unary operators, such as the square root operator, you just need to pop 1 operand. Finally, pop the token out of the stack and use it as the final result. Let's go through the algorithm with the postfix expression we have. The first 3 tokens are all operands, and we push them into the stack. The fourth token is a multiplication operator. In this case, we pop 2 operands, 2 and 3, out of the stack and multiply them. We then push the result 6 back to the stack. We can proceed with the same process. After handling all tokens, the stack should contain only one operand. In our case, the operand is 9, which will be popped and used as the final result. And we can easily verify that the result is correct. In summary, this video we have discussed an algorithm for parsing and calculating arithmetic expression. The algorithm contains 3 steps: tokenization, infix-postfix conversion, and postfix calculation. The second infix-postfix conversion step uses a stack for caching operators, while the third postfix calculation step uses a stack for caching operands. This is the last video for the cube and stack module. In the next module, we will discuss the hash table data structure. Thanks for watching and see you next time.